Hello, everyone. Welcome back. Today, we're going to be talking about the properties of normal distributions. Now, let me tell you, this is a really important topic. Normal distributions come up so much in statistics. Statisticians love normal distributions, or at least they use them a lot, because it's a pretty cool discovery in statistics. So, we're going to be talking about them today. So, what is a normal distribution? So, a normal distribution is actually the most common continuous probability distribution. It's also known as a bell curve. If we hear bell curve or bell shaped curve, then that means normal distribution. A normal distribution has a mean, mu, and a variance of sigma squared, and it's denoted this way, right? Where we have x and the little squiggly line, and then n for normal distribution, and then we have the variables mu and sigma squared. Okay, so, what are the key characteristics about the normal distribution? The first rule I want to talk about is called the empirical rule or empirical formula. It's also known as the 68 95 99.7 rule. And you know what? That's the way I want to teach it here, because that 68 95 99.7 rule helps you remember what the rule actually is, and that's a positive thing. So, let's call this rule the 68, 95, 99.7 rule. And what this rule states is that from the mean to one standard deviation away is 68%, right? Is 68% of the total data, right? Now, what about two standard deviations away? All of this, when we're two standard deviations away, this is 95%. I'm just realizing it says that here, so I don't necessarily need to write it myself. But from there to there, two standard deviations away on both sides is 95%. Now, what about three standard deviations away? That is going to be 99.7%. So basically, all of the data, almost everything is there. There's only this tiny, teeny little bit over here and tiny, teeny little bit over here, but this accounts for, those two combined only count for 0.3% of the overall data, right? So only 0.15% for each one, right? Very, very little. And so using this rule, we can find out a lot of stuff, right? Let's say we're asked, how much of the data is represented? What's the probability of being from here to here? Well, we could say, okay, well, we know it's symmetrical, and we know that this in total is 68%. So half of this would be 34% of the overall data, right? Let's say we're asked, what's the probability that we're over here or above, right? All of this shaded stuff. Well, we could say, oh, well, we know that all of this is 95%, right? And then we know that this area over here and this area combined are both equal, and they're both going to be 5% together. So that means each of them is 2.5%, right? So 95% plus 2.5% is 95.5%, right? So we could figure it out like that. Or, we can use similar logic with this rule, and also just what we know in general about symmetric distributions as a whole, to figure out a lot of stuff from this rule. Now, let's say that I ask about this number. What about this number between these two and everything above it? For that, we're actually going to need Z. We're going to need to learn more stuff than we've learned so far. We're going to need to know about what are Z scores and how to use the Z score tables as well. But there is a way to do that too. And one thing I want to mention is you never have to memorize the Z score table. I will never expect that, nor will anyone ever, no matter how far in math you go, no matter how far of a level up you get to in your mathematics career, that you will never be expected to memorize that. But it is good to know these three numbers, right? It's a lot easier to measure, to be able to remember three numbers than tons and tons and tons of numbers, right? So, do remember these three numbers, which are 68, 95, and 99.7. Good. Very good. Okay. So here it says a specific normal distribution where we have z and then little squiggly n 0 comma 1 is called the standard normal distribution. So what does that mean? That means if the mean is 0 and the standard deviation squared is 1, then that's the standard normal distribution. And probabilities involving the standard normal distribution can be found using the areas under a standard normal distribution table. Okay, so let's actually head to that. Here's the areas under a standard normal curve, right? We can use this here. So we can find the z-score, which we don't know how to do. We can find the z-score. Let's say it's 1.23. We'd say 1.2 is here, and then 0.03 is there. So it would be that number, and we can say, oh, it's 89.07%, for example. And the opposite is true. Let's say we know the probability is 0.6736. Well, we've got to find that number here on the table, and we can find the z-score. We can say, oh, the z-score of that is 0.45. So basically, long story short, we can use this table. We can use this table in order to figure out, what's the area under the curve in any of these places. Now, how can we find that out algebraically using math techniques? Well, we need calculus to do that. And so that is why that's another reason we're using this table, is because calculus does not come up in this course. We should just use the table rather than using calculus. Very good. Okay. So let's do some examples. Let's talk about how can we figure out these probabilities. Well, we need to find the z-score for these probabilities, which I should explain how to do that in a moment here as well, because we haven't actually gone over like how to find the z-scores. So in order to find the z-score, what we must do is we must take the number minus mu over the standard deviation, right? And so for a standard normal, where we have the mu of 0 and the standard deviation of 1, this is just going to equal to x for our standard normal, right? And that's why it's called standard normal. And I want to point that out because oftentimes what will happen is students will see, oh, look, it's, z less than this value, and they'll just go straight to this value and find it in the z table, and that'll be correct. And in these cases, that will always be correct. That's true because it's standard normal. For non-standard normals, it's going to be a little bit trickier. We're going to actually have to plug in our mu and our standard deviation. And to be clear, here we're doing that too. It's just that our mu is 1 and our mu is 0 and our standard deviation is 1, and so therefore it's just going to give us the same thing back. Okay, so let's do this case here. We want to know the probability z is less than 1.65. So let's go to our table and find that out. Okay, 1.65. So here's 1.6. Let me circle that. And then here's 5 right here. So the answer is this number here, 0.9505. So let's do it. 0.9505. And there we have it. Now here's this one. It says, what's the probability that the z-score is less than -1 on the standard normal? Okay, so here's positives. Here's our negatives. So -1 is this one right here. It's going to be 0.1587. So let's do it. 0.1587. And there we go. All right, what's the probability that our z-score is -0.5? This one is greater than -0.5. So to be clear, this is going to be the same as 1 subtracted from the opposite. 1 subtracted from the probability that z is less than -0.5. And if we go back to our z table, let's find -0.5. That's going to be here. right? Negative 0.5 is 0.3085. So our answer here is 1 minus 0.3085. And if we punch that in our calculator, we're going to end up with 0.6915. And that's that. Very good. Okay, the next one here is asking what's the probability it's between 1.65 and negative 0.5? So that's a good question. And let's think about that. Basically, how would we determine that? Well, we know that the probability of from here down, let's say this is 1.65. We know the probability from here down, all of this, is going to be 0.9505, and we want to subtract off the place where it's less than the place where it's less than negative 0.5, right? So let's say this is negative 0.5. We want to subtract off this piece. So this basically is going to be the probability that it's less than, that z is less than 1.65 minus the probability that z is less than negative 0.5, right? And over here, we found out the probability of being less than negative than 1.65 rather is 0.9505. And then over here, we found out the probability of being less than negative 0.5 is 0.3085. So therefore, our answer would be 0.642, right? Because in the general case, we can take this whole thing, and we can subtract off this part of it here, right? The part of it that is less than the amount that we can own, that we're stopping at, our stopping point there. And we can do that, and we can get the desired amount. We can get this portion of the graph, right? So just a little bit of forethought there is going to help us find, the probability between those values. Now, something I mentioned earlier is that in general, we can't just take the z-score and assume that, that's good. In general, we need to find the z-score not from the x value, but from here, right? And so basically, this is going to take whatever x values we have and say, oh, here's where they would be on the standard normal, right? By subtracting the mu and going over the standard deviation, we're going to get it to that same spot on the standard normal so we can find the probability, because the probabilities under the curves, whether we have a standard normal or not, are going to be the same. All normal distributions are the exact same with the exception of the scale we're going on. The scale changes, but the actual probabilities don't change on any normal distribution ever, which is the nice thing. And that's why that table we use there, we can actually use for things that are not the standard normal, so long as we first find the appropriate z-score that caters to that standard normal, right? But we need to adjust our numbers to find the correct z-score in order to be able to use that table. Okay, so let's do some more examples here. This one says to find the probability that is from a normal distribution, but not a standard normal, we must use this formula, which is what I was talking about just a moment ago. And so if we don't have a standard normal, we can still actually use that same exact table. We just need to, we need to adjust those numbers. So let's give an example of us doing that. Here we want to know if we can find where x is less than 1.2, but where our normal has a mean of a mu of 3 and a standard deviation or a variance of 9. Well, first of all, to find the standard deviation, we need to take the square root of the variance, which is going to give us 3, right? So mu and standard deviation are both 3. And we're starting at number 1.2. So the z-score is going to be 1.2 minus 3 over 3, which is going to be, this is negative 3. My apologies. This would be negative negative 3, which would be plus 3. This is going to be 4.2 over 3, which is 1.4. So if the z-score is 1.4, then what is the probability that x is less than 1.2? Well, we need to find the z-score, the probability for the z-score of 1.4 to do that. So let's go back. Let's go to 1.4, and looks like the answer is 0.9192 if we go to our z-score. And so that's the answer, 0.9192. And there we have it. Good. So let's review what were the steps we had to do. We first had to figure out what the appropriate z-score was on the standard normal from this example that doesn't use standard normal by using this new z-score equation. Then we said, okay, if that's the associative z-score, then let's go find the probability that's associated with the z-score from our table, and then that's going to be our answer. Very good. All right, and here's a word problem that's very much asking the same thing. Actually, here's a couple word problem examples we'll go over. This one says, on a particular math assignment, the class average was 75% and the standard deviation was 7%. Find the probability that any given student received a mark higher than 80. So basically, if we randomly select a student, what's the probability that that student received higher than an 80% given the class average and the standard deviation? So first of all, let's write what's given. Well, we know that mu is 75%, right? Because 75% was the average or mean grade of these students on this math assignment. The standard deviation is 7%. Now we don't have to square root this because this is already a standard deviation. They didn't give us the variance. If they give us the variance, we have to take the square root to find the standard deviation. But here they already gave us standard deviation, so that's no problem. And we want to know, what's the x we're trying to figure out? We want to know the probability that somebody got higher than an 80. So our z-score in this situation would be 80 minus 75 over 7, which is going to be 5 over 7, which is going to be 0.714. Okay, so that means the probability of x being greater than 80 is the same as the probability that associated with the z-score being greater than 0.714. And as we know, the table we're using only says what's less, right? So this is going to be the same as 1 minus the probability that the z-score is less than 0.714, which is going to be 1 minus, well, I'm not sure. Let's go find it out. 0.714. Let's go there. 0.7. Okay, here's 0.7 and here's 0.71, right, because we have 0.01 there. So it doesn't actually, technically the 4 we just kind of have to throw out. So this isn't 100% accurate, but this is going to be our best estimate. So let's go with this. 0.7611 is what we'll go with. Right? Because that's going to be closest if we round down. Now we would have to round up if we had a number greater than 4. So if we had 0.719, we would round that up to 0.72. In this case, it's 4, so we round down. And then we're going to get, as our answer, 0.2389. So the probability of a randomly selected student getting a mark higher than 80% would be 0.2389. So 23.89% of the students overall on this math assignment got a mark higher than 80%. So yeah, a little less than a fourth of the class overall. Very good. All right, let's do one last example for today. This one says a machine that fills boxes of Smarties has a mean of 55 grams and a standard deviation of 4 grams. What is the probability that any given Smartie box has between 50 and 57 grams, right? Because to fill the boxes of Smarties, you got to figure they don't actually have someone do it by hand, probably. They probably just have some machine that distributes them, right? And the machine is relatively accurate. Most of the time it's about 55 grams, but it could vary a little bit, right? Not every box of Smarties is going to have exactly the same content necessarily, even though ideally they would. They probably don't. So let's figure this one out. We need to find two different Z scores, right? We need to find the Z score for 50 and the Z score for 57 because we want the probability that our answer is between 50 and 57. So let's find Z score 1. Z score 1 is going to be x1 minus the mean over the standard deviation. And let's just say this is x1 and this is x2. And then Z score number 2 is going to be equal to x2 minus the mean over the standard deviation. Very good. So what is our mu? Our mu is 55. It says there's a mean of 55 grams and a standard deviation of 4 grams. And then x1 is 50, we said. That's how we defined it. And x2 is 57 because that's how we defined it as well. Okay, so Z1 is going to be 50 minus 55 over the standard deviation, which is 4. So that's going to be negative 5 over 4, which is equal to negative 1.25. And then over here we have x2, which is 57, minus 55 over 4, which is 2 over 4, which is 0.5. So what are we looking for here? Basically, what we're looking for here is the probability that our Z score is between negative 1.25 and 0.5. Oh, sorry, I shouldn't put X here anymore. I should put Z, right? Because we calculated that these are the associated Z score. These are the Z scores associated with the Smartie box having between 50 grams and 57 grams, given what we know. Very good. Okay, so let's do that. Well, first of all, what do we need to find? We need to first find the probability that its Z is less than 0.5 minus the probability that Z is less than 1.25 or negative 1.25. Sorry. Okay. And that is going to be equal to what? Well, let's find out. Let's go find out. So we need the two numbers we have to remember are 0.5 and negative 1.25. So let's head to our table. The first one was 0.5, so that's going to be associated with 0.6915. And the second one was negative 1.25. So negative 1.2 is here. And then 5 is over here. So it's going to be that one right there, 0.1056. So now let's go plug those values in now that we found them. So that's going to be 0.6915 minus 0.1056. And graphically, if we kind of, draw a sketch of the graph, right? Let's say from this point forward, this is 0.6915. And then this part, this part over here is less than negative 1.25, relatively, right? We're switching this over to the standard normal in order to figure it out. Then what do we have left? We have this part left. We have the in-between part left, and that's exactly what we want to find out. We want to make sure that it's more than 50 grams, but less than 57. It's very important. Good. Okay, so what's the answer going to be? The answer is going to be 0.5859. So there's about a 58.59% chance that any randomly chosen box has between 50 grams of Smarties and 57 grams of Smarties. So more often than not, this is going to be the case. It's going to be within that range. All right, well, very good work today, everyone, and I will see everybody next class. Next class, we're going to be talking about normal sampling and modeling. So, we're going to continue to talk about normal distributions, and spoiler, a lot of this, the stuff we're doing moving forward, has to do with normal distributions. The rest of this unit is just more about normal distributions. It's a huge topic, and that's what the entire unit here is about. So have a good rest of your day, everyone, and we'll see everybody next day to talk more about normal distributions. Bye, everyone.